In this video, we continue our study of inverse trig functions. We're just doing some of the types of problems that we did in units 1 through 4, but we're applying them specifically to inverse trig functions. This problem can be solved as a related rates problem, or it can be solved in terms of a derivative of an inverse trig function. And this is exercise 97 from section 5.6 of the Larson Calculus text 10th edition. The question says, an airplane flies at an altitude of 5 miles toward a point directly over an observer. So we'll just say this is the ground. Here's our observer. And we've got a plane right here. I don't know how to draw a plane, so I'm just going to call that a plane. And that plane is flying 5 miles above the observer. And then the question says, consider the angle of elevation theta and the horizontal distance x from the observer to a point directly below the plane. So we're calling this x. And then the angle of elevation is from that person's feet. We make a line segment from that person's feet to the plane. And the angle of elevation is that angle right there. First, we're asked to write the angle of elevation as a function of x, and then we're told that the speed of the plane is 400 miles per hour. So the plane is coming towards us at 400 miles per hour. And we're asked to find d theta dt when x equals 10 miles and when x equals 3 miles. Say, okay, well, there are a couple of ways that we can do this. I'm interested in theta as a function of x. And I see I've got a right triangle here. Now, the side opposite theta is 5 when the side adjacent to theta is x. Since we have the opposite side and the adjacent side, we can use either the tangent of theta or the cotangent of theta. Either one is fine. I don't remember what I did in the Desmos page, but if we use tangent of theta, we'll say that tangent of theta is, if we use SOHCAHTOA, tangent is opposite over adjacent. It's that ratio of the opposite side to the adjacent side relative to that angle theta. And the side opposite theta is 5 miles when the side adjacent to theta is x miles. So we're asked to find theta as a function of x. So if we want to, we can solve this for theta by taking the inverse tangent of both sides. The inverse tangent of the tangent is going to give us theta as long as theta is in the appropriate range of values. So as long as theta is between negative pi over 2 and pi over 2, the inverse tangent of the tangent of theta is theta. And I'll just call that the arctangent. We'll have theta equals arctangent of 5 divided by x, where we're assuming that theta is in the interval from, negative pi over 2 to pi over 2. So that's one possibility. Now the other possibility is that we could say, instead of using tangent, since we have the opposite and adjacent sides, we could use cotangent. Cotangent is the reciprocal of tangent. Cotangent, since it's the reciprocal of tangent, if tangent is opposite over adjacent, cotangent is adjacent over opposite. So the adjacent side adjacent to theta, that's the side next to theta that is not the hypotenuse, is x. When the opposite side is 5, that's x miles to 5 miles. So if we want to, we can solve for theta by taking the inverse cotangent of both sides, or the arccotangent. So we have the arccotangent of x over 5, but we have to choose theta to be in the correct interval in order for that to be true. So the arccotangent of cotangent of theta is just theta as long as theta is on the interval from 0 to pi. Now, when we look at this graph, we think about a plane flying over an observer. So our angle of elevation is theta, and let's say that the plane is in front of us and sort of coming towards us, at least, but it's not coming directly towards us. It's on a parallel line sort of above us, a line parallel to the ground. And it's 5 miles above the ground the entire time. Now, as I watch that plane, as it continues to get closer and closer to me, that angle theta increases. And if at some point theta is equal to pi over 2 or 90 degrees, then the plane's going to be right above me. And then as the plane continues to go past me, that angle theta, well, I guess technically the angle of elevation at that point would be measured from the other side. But if I'm still trying to measure it from the positive x-axis, that angle theta would be between 90 and 180 degrees. So if we use that convention that we're measuring this theta, angle of elevation from the positive x-axis, and we're thinking of our observer as standing at the origin, so we actually have added a y-axis right here, and then this is the x-axis, then it might make more sense to use the cotangent function as opposed to using, or the arccotangent function as opposed to using the arctangent function, because with arctangent, we get angles between negative pi over 2 and pi over 2, and we're never going to have a negative angle here. The plane is always above us, it's never below us. So that's not, that negative value doesn't really make sense. But it does actually make sense to think of that angle as being between 0 and pi. If that plane continues to fly over us and fly past us, then we can say that angle goes past a 90 degrees and then over into the 90 to 180 degree range. So we'll say that, and maybe we'll reword this. Instead of saying angle of elevation, we'll say the angle theta say measured from the positive x-axis. We want to write that angle of elevation measured from the positive x-axis as a function of x. So that's what we have. Theta as a function of x is arccotangent of x divided by 5. Okay. And then in part B, we're told that the speed of the plane is 400 miles per hour. So the plane is flying over us like this. Now that 400 miles per hour indicates we're talking about a rate of change, and it's some change in distance per unit time. So that's actually giving us a dx dt. This distance here from the plane to this point, 5 miles above this observer's head, is the same as this distance here. And as that plane gets closer and closer to us, as like time increases, x decreases the whole time because that plane is going to get closer to us, so x is getting smaller. If that's the case, the fact that the speed of the plane is 400 miles per hour indicates that dx dt is not 400 miles per hour, but it's negative 400 miles per hour because that change in x, or that x value, is decreasing. So we know that dx dt is negative 400 miles per hour, and we're asked to find d theta dt at x equals 10 miles and x equals 3 miles. Now we can do all of this on paper, and we can also do this on Desmos. I'd like to show you a picture just to get a better sense of it. I drew this picture here, but it's static. It's cooler to look at the pictures on Desmos. So let's do that. So this is our little Desmos graph. And we've graphed the point 0, 0 and placed an observer there. We have graphed a plane 5 miles above ground level. And then x is just this purple distance, the distance from here to here. In this picture right now, x is 15. And since I wanted my x value to shrink as time increased, I used 15 minus x naught, and I'm letting x naught go from 0 to 15. So that the x value, as x goes from 0 to 15, 15 minus x goes from 15 back to 0. So if we play this now, we can see what happens. That plane is flying above us, 5 miles above ground level at 400 miles per hour. We can see that as time changes, x is shrinking, so dx dt is negative. Dx dt is at negative 400 miles per hour. And at the same time, that angle theta is increasing. It's hard to label on the graph, but we can see our theta was, let's see, at the beginning, it would have been the tangent of theta would have been 5 divided by 15, or tangent of theta would be 1/3, so theta would be the arctangent of 1/3. And then as time increases, actually, we should probably do it that way. As time increases, that x decreases. I think I'm going to do that. I'm going to call that. I was going to use that as a function of t, but I won't. Never mind. I was thinking that rather than using x equals 15 minus x naught, we could use x equals 15 minus t, or t naught. But maybe not. Maybe we shouldn't. Just keep going like that. So that's a situation. And speed it up a little bit. And actually, maybe we should look at the value of theta the whole time. So we know that theta is, as a function of x, is the arc cotangent of the adjacent side, which is x, divided by 5. And maybe what we want is arc cotangent, or we want theta of x naught. Okay. They don't want us to use that as a parameter. Won't let us do that. Let's do that. Okay, so that is our angle and radian measure. Let's multiply by 180 and divide by pi. So we see that the angle is 60 degrees approximately. When theta, or when we're at 15 here, our angle is the arc cotangent of 15 divided by 5, or the arc cotangent of 3, or if you prefer, the arctangent of 1/3. I always think in terms of tangent, cotangent, or it's tangent, sine, and cosine. So our tangent, or at this point, when the y value is 5 and the x value is 15, we have our theta is the arctangent of 1/3, which is 0.32 radians. If we multiply by 180 and divide by pi, we get, it's about 18 degrees. And then if we want to, we can see how this value changes as that x value increase, or that x value decreases. And what did we have? We're going to have the tangent is opposite over adjacent, so we're going to have 5. Is that opposite side? The side opposite our theta is always 5. That doesn't change. And then the denominator is x naught. And so it says that we've got 90 degrees there. That doesn't look right. Oh, sorry, it's not x naught. It's 15 minus x naught. Because x naught is 0 here. When x naught is 0, this distance is actually 15. So at 18 degrees there, and 18 degrees there. Say, okay, let's let x increase. As x increases, we see that the theta value increases as well. Or as x naught increases, which means x actually decreases. Would it make more sense to write this in terms of time? Probably would, but we have to be careful. But you can see when x equals 10, or x naught equals 10, this length is 5 and this length is 5. So that's just a 45, 45, 90 triangle. So the angle is 45 degrees. I've got a love bug here. We can see that that angle is increasing as our plane gets closer and closer to us, the angle increases. When the plane's directly over our heads, the angle is 90 degrees. All right. So we know that's true. So they say find the angle of elevation theta as a function of x. I used arctangent. We use arctangent. The graph looks like this. That's y equals the arctangent of x in general. It's that orange dotted line. But in the angle that we're actually interested in starts at x equals, excuse me, that function that we're actually interested in is only defined on a particular domain. We want x to start at 0 and end at this value of x over here. That value of x, I've been using 15 minus x naught, and then letting, as x naught increases, that plane gets closer to us, so x actually shrinks. So if we run the animation again, that orange function is arctangent of x. Or arctangent of what? 5 divided by x. Now, if you want to, I guess we could have allowed the x values to go beyond 15. So let's go to 30. Then the graph would look like this. But now it's not graphing that line segment from the observer to the plane. So if I wanted to graph that line segment from the plane to the observer, I'm just going to use the same equation. That still work. But my x's are going to go from 15 minus x naught to, to 0, I think. Yeah, there it is. I typed 1 by accident. Go to 0. There we go. So as x increases, or as x naught increases, that plane gets closer to us. So it's just flying over our heads, and then we look at it above our heads, and then we look behind us. And that angle theta is measured from the positive x-axis to that point. So we're going, theta is actually going from 0 to some number that's larger. Now, one thing I want you to notice is that when we're over here in this region where theta is between 90 and 180, the arctangent is giving us the wrong answer. It's giving us an angle that's negative 30 degrees, which is in quadrant 4. We want the angle over here between 90 degrees and 180 degrees. The arccotangent gives us that angle. And that's because of the restrictions that we made on the cotangent function when we defined the arccotangent in the first place. The same is true for the arctangent. Remember, we restricted ourselves to the interval from negative 90 degrees to 90 degrees. So the arctangent is always going to give us values, or always going to give us angles between negative 90 degrees and 90 degrees if we convert to degrees by multiplying by that 180 over pi. But the arccotangent is always going to return angles between 0 and pi. Since we're looking for an angle between 0 and pi, it makes more sense, to use the arccotangent function as opposed to using the arctangent function. Although we could use the arctangent function, we just have to remember to add 180 degrees or 9 or pi over 2, or pi radians to the arctangent function when we're done. Hope that makes sense. I just wish I could label the angle here. I don't know how to do that. But as it stands right now, this orange graph is the arctangent graph. I think I want everything in terms of arccotangent instead. So we'll copy and paste this. There's absolutely nothing wrong with using that arctangent function to write the angle of elevation theta as a function of x. But remember, with cotangent, you're going to take the reciprocal. So instead of having a 5 over x, you're going to have an x over 5, adjacent over opposite instead of opposite over adjacent. So this is the arccotangent graph. One thing you might notice, if you look at this, is that the arctangent graph has a particular range. We add some tick marks there. Oh, I guess we need to go from, let's use multiples of pi over 2. So that arctangent is giving us values between negative pi over 2 and pi over 2. And then we say we're just, instead of being interested in the whole thing, we're interested in just this piece. Still giving me a hard time. Looks like that. But if I switch to the arccotangent, instead of having a range of negative pi over 2 to pi over 2, our function has a range of 0 to pi. So it looks like that. Has that horizontal asymptote y equals pi. And let's make that dotted. We don't want the whole arccotangent graph. We just want part of the arccotangent graph. Actually, the arccotangent, we probably want the whole graph, don't we? No, we're interested in it on a finite interval. That's right. From negative x to x, essentially. I think. Maybe I'm wrong about that. But we've got our arccotangent of x over 5 is right here. Now, if you want to compare the arctangent and the arccotangent, you can look at this. Look what happens. There's arctangent. And then if I add the cotangent to that, we see that the arccotangent, it just continues that branch of the tangent function, or the arccotangent function. We get the same values on that interval from 0 to infinity. But with the arccotangent, rather than having a branch down here from negative pi over 2 to, or where our y values are between negative pi over 2 and 0, the rest of the branch is up here where the y values are between pi over 2 and pi. That makes sense. Okay, so let's do everything in terms of arccotangent instead. Now we're told that the speed of the plane is 400 miles per hour. Find d theta dt when x equals 10 miles and x equals 3 miles. So we're going to use the chain rule. Now, we're taking the derivative of arccotangent of x over 5. So I'm going to do this calculation again. Now, the derivative of arccotangent is -1 divided by the inside function squared plus 1. Now our inside function is x divided by 5, so I can substitute x divided by 5 here. And then I want to multiply by the derivative of the inside by the chain rule. Oops. And x divided by 5 is just the same as 1/5 x. So if I take the derivative of 1/5 x, I'm just multiplying by a 1/5, right? So we'll have this equals this. And the derivative of 1/5 x is just 1/5. So you're imagining taking this larger fraction and multiplying it by that 1/5 there. Now notice that we've got that x divided by 5 squared. When we square that, we're going to have x squared divided by 5 squared. So we're going to have a 25 in the denominator. So it'd really be nice to multiply this entire expression by 25 divided by 25 in order to get rid of that 5 squared in the denominator so we don't have fractions within a fraction. We've already got an extra 5 here, so I'd like to multiply by another 5 in that denominator. But if I did, I would change the value of the fraction. So what we're going to do is we're going to multiply by a well-chosen 1, which is 5 over 5. And then this is what we get. We'll have a negative 1 times 1 times 5, so negative 5 in the numerator, divided by x squared divided by 25 times 25 was just x squared. Oops. And then we're adding 5 squared times 1, so 25. So we've got negative 5 divided by the quantity x squared plus 25 is our theta or theta prime of x. So the change in theta as x changes. We see that it's negative all the time. Now you might think that seems wrong. Whenever I look at this picture, it's obvious that theta is increasing, right? That was one of the first things that I thought when I was looking at my graph. Like intuitively, that seems wrong. Right? Theta is increasing. So we're measuring it from the positive x-axis. Rather than using the angle of elevation, we're going to measure it from the positive x-axis. You might say, well then what's wrong with our assumptions? If theta is actually increasing, let's just go from 0 to 15. Theta just went from what was it? Some number of degrees, like 18 degrees or so, to 90. You find the flaw in the logic? One thing I want you to remember is whenever you take the derivative of something, so in our case, we're taking the derivative with respect to x. This is telling you how theta changes as x increases. So as I go from x equals, say, 5, I tried to add more tick marks on the axis, but it wouldn't let me. Let's say we're starting at x equals 10, and we want to know how does theta change as x goes from 10 to 11. So we start at x equals 10, and then we go to x equals 11. What happens to the angle as x increases from 10 to 11? We can see that the angle is actually decreasing. As x continues to increase, that angle decreases, right? If the plane was flying, instead of flying towards us, if it was flying away from us, it's flying the other way, that angle of elevation would continue to decrease as the plane goes farther and farther to the right. But that's not what's happening. Instead of that, the plane is actually coming towards us. Since the plane is coming towards us, the change in x is actually negative. So if I have a d theta dx, which is another notation for this, so we could call this d theta dx. And this is the change in theta as x changes. That is a change in theta as x increases at a particular point. If x happens to decrease, this change in theta is going to have this change in theta with respect to x is going to have the opposite sign. So even though it seems like this is always negative and that's counterintuitive, it actually is, it should be consistent with our expectations if we imagine continuing to increase our x values, so the plane moving to the right rather than to the left. The y values on the graph of that cotangent function, look at them. The y values continue to decrease as x increases. And we can also see, if we look at that angle of elevation, that as the plane moves farther to the right, the angle of elevation decreases. that when the plane is directly over us, it's 90 degrees, or the angle of elevation is 90, and then as the plane moves farther and farther to the right, that angle decreases. So here, the cotangent is going to give us an angle of pi over 2 radians, or 90 degrees. And then that angle continues to decrease. And if you want, you're like, what does that mean? Or how is it going to decrease? You can actually look at the values. And again, I have a tendency to think in degrees. They were starting at 90 degrees, and then as theta, or as x increases, we see that the y values on the graph of the arctangent and arccotangent continue to decrease. It goes from 90 degrees here to 18.43 degrees on the end. And of course, we could use radians, and it would be whatever that fraction is right there. I don't know what that y value is as a fraction in radians. Okay. Okay, so we computed our derivative just using the derivative of the arccotangent function and the chain rule. Now, if we had taken the derivative of the arctangent function, it would have given us the same result, the same theta prime of x, but it would have involved a little bit more work. Because in the case with the arctangent, the x is actually in the denominator. So when we take the derivative, we'd have positive 1 over 5 divided by x quantity squared plus 1. Actually, let's take the derivative of this one now. Just as practice. It's always a good idea. Well, I just want to show that you get the same thing. So this is the other theta. I wish I could use a different angle. Maybe we'll use alpha. Alpha as a function of x is arctangent. I don't know. Just to have a different letter. Then alpha prime would require the chain rule. So we take the derivative of arctangent first. So we have 1 divided by the inside function squared. Whoops. Add 1, and then you multiply by the derivative of the inside by the chain rule. Now that 5 divided by x is 5 times x to the negative 1. We can bring that x to the numerator. That way we can use the power rule. Don't forget to put the inside function back inside. If we take the derivative of 5 times x to the negative 1, well, what do we get? Well, the first expression stays the same. With that 5 divided by x squared, I'll square the numerator, get 25. Square the denominator, I'll get x squared. So we have all of that times the derivative of 5 times x to the negative 1, which is 5 times negative 1, which is negative 5, times x to the negative 2. And x to the negative 2 actually gives us an x squared in the denominator. So that's the derivative of the inside. And if we distribute, just multiply straight across, we have negative 5 in the numerator divided by 25 plus x squared in the denominator. So we see that the derivatives are the same. The rates of change are exactly the same. But the only difference is when we look at the arctangent graph, the arctangent gives us values between negative pi over 2 and pi over 2, whereas the function of theta gives us values, or theta as a function of x, where that's our cotangent function gives us values between 0 and pi. So I prefer that one in terms of 0 and pi. But it's a good practice to do the differentiation. All right. Now, what did the question say? The speed of the plane is 400 miles per hour. Find d theta dt when x equals 10 miles and when x equals 3 miles. Well, we have d theta dx. We know it's negative 5 divided by 25 plus x squared. And we want d theta dt at x equals 10 miles and at x equals 3 miles. So what we'll do is we'll compute theta prime, that's with respect to x, and evaluate it at x equals 10. And then we'll multiply by dx dt. Well, dx dt is that negative 400 miles per hour that we were given in the problem statement. We're told that that plane is flying towards us. And if that plane is flying towards us at 400 miles per hour, that x value is shrinking. So that dx dt is negative 400 miles per hour, and we multiply it by d theta dx in order to get d theta dt. We'll do that on paper, and then we'll compare our calculations on paper to the values on Desmos. So we have d theta dt equals d theta dx, evaluated at x equals a particular value, I'll just call it x naught, times dx dt. So we're going to have negative 5 divided by 25 plus x squared times dx dt, which is negative 400. Actually, let's include the units. This is some number of radians per mile. That's our d theta dx. So as x increases by 1 mile, theta changes by this number of radians when x equals x naught. And then, or actually, maybe I shouldn't use x equals x naught. Let's just say x equals some particular value, some number. So we're going to plug that number in right here, okay? So you have some number of radians per mile, and then we're multiplying by that negative 400 miles per hour. And then you can see that the miles reduce, and we get some number of radians per hour. Say, okay, well, what is that at x equals 10 and x equals 3? We have d theta dx at x equals 10 times dx dt. That's just negative 5 divided by 25 plus x squared times negative 400. So we get 2,000 divided by 25 plus x squared, 10 squared in this case. So we end up with 2,000 divided by, that's 125. I think that was 16, actually. And that's going to be radians per hour. So as the hours increase, if we wait 1 hour, then theta would increase by 16 radians. And I'd say, why would I measure everything in hours? The only reason we're measuring everything in some number of radians per hour is because the speed of the plane was given in miles per hour. It actually might be more useful to change to minutes or seconds and by multiplying by the appropriate conversion factor. But this is what we get when x equals 10. And then we're also asked to answer the same question when x equals 3. So nothing has really changed. This times this is still 2,000. We have 25 plus x squared in the denominator. And evaluate at 3. So we have 25 plus 9. What is that, 34? I actually don't know what that value is, but it's some number of radians per hour. One thing I want you to notice is that when we multiply by that dx dt, which is negative, our negative change in theta with respect to x and the negative change in x with respect to t cancel, and we end up with a positive answer. So as that plane moves closer to us, we see that theta increases as time increases. And that's consistent with our expectations. That's consistent with what we see when we graph the situation where that plane is flying towards us online. So let's get a decimal approximation of this. We'll look at that on Desmos again and make sure everything is consistent with our expectations. So at x equals 10, theta dx is negative 0.4. So that means the number of radians is actually decreasing at 0.4 radians per hour as x goes from 10 to 11. So x is 10 here, x is 11 a little bit farther to the right of that. If x were to go from 10 to 11, the theta value would decrease by 0.04 radians per hour. Or not, sorry, not per hour, per mile approximately. So we're going from 10 miles away from the observer to 11 miles away from the observer. And then you say, okay, well, if I I'm looking for the change in theta with respect to time, and x is actually shrinking at a rate of 400 miles per hour, then I have to multiply by that's negative 400. That negative 400 times that negative 0.04 gives us 16 radians per hour, which is consistent with our expectations. That theta value is increasing as x increases, or excuse me, as time increases. So d theta dt is positive as we would expect, and d theta dx is negative as we would expect as well. Initially, that might seem counterintuitive, but again, you have to look at the picture. You have to think about what happens to theta as x increases. And when x increases, we see that the value of theta is decreasing. We can also look at the values of theta on the graph. The value of theta is actually given by the point of intersection between this green line segment and the curve, the arc cotangent of, what was that? X divided by 5. So the angle in radian measure is right there. If we wanted to, we could plot that point. So we'd have x is given by 15 minus x naught. And then we're taking the arc cotangent of the x value, which is 15 minus x naught, divided by, that's the adjacent side, divided by the opposite side. And I'm just using 15 minus x naught so we can continue to use our slider. They say when x is 2.9 miles, the angle is 1.04521 radians, which we can convert to degree measures so that it makes a little bit more sense to us intuitively. It's about 59 degrees. All right, so we did that at theta, or x equals 10. Now we might also be interested in the change in theta with respect to time when x equals 3 miles. So we change our x value to 3. Trying to find my x naught. So x naught is 12. Here x is 3, and I'm interested in the change in theta with respect to time as x goes, or as time increases. But initially, we compute that theta prime with respect to x, so change in theta with respect to x. So as x goes from 3 to 4, we're saying how much, or what is the instantaneous rate of change at x equals 3? What is the slope of the tangent line at that particular value? Well, if we wanted to, we could graph that tangent curve, or not the tangent. Well, yeah, it's the tangent curve. But it's we could graph the derivative theta prime and see what that value is of theta prime. We'd see that the value is negative 0.147, which is again telling us that the theta value is decreasing by 0.147 radians per mile at that point. Or if you want, you can multiply by 180 and divide by pi. So that means the theta value is decreasing by negative 8.4 degrees per mile at that point. If you take that and you multiply by that negative 400 miles per hour, because the plane is coming towards us, then you have the change in theta with respect to time. And so we get 58.8 radians per unit time or per hour. Or if you prefer, you can again multiply by that 180 divided by pi, and you get a lot of rate, or you have a lot of degrees, 3,370 degrees per hour. So I guess, I mean, maybe that doesn't make sense because you're imagining like going around and around and around, and that's not what we want. I think it's because of those units of measuring time in hours as opposed to measuring time in minutes or seconds. But technically, like that is the answer. It's 58.8 radians per hour, or negative 0.147 radians per mile. So as our miles increase, the beta values decrease, as we can see on the graph. But if our plane is flying towards us, then we take the negative and multiply them together to get something positive. I just like using the slider. Here's the plane flying toward us. Oh, actually, it should be x naught between 0 and 30. That's what I wanted to do.